So I showed you the classification scheme from before. This is the classification scheme we're using for this particular project. You can see we're getting much more detailed, right down to the species level in some instances. But these are the habitats that they're most interested in trying to extract from the imagery. Pans and pools especially, so they can really understand how those marshes are evolving fairly quickly over time. So in terms of the source data we needed for this project and for all similar projects, we're looking for a high-resolution imagery source. In this case, we're using ADS-40 data. It's a 4-band product, so we can use the NIR band. It's a 0.5 meter spatial resolution, which is more than enough. In fact, in some cases, we resample that to 1 meter just to make the processing easier, especially at a statewide scale. But we're going with a 0.5 meter resolution. It was acquired for another project completely, so it's a nice return on that investment. We're able to use it multiple times. We developed several derivatives from the imagery alone, and then those were all fed into eCognition so that we could extract statistics, again, for each of those polygons based on these derivatives, NDVI, tasseled cap, and principal component. And then we went and we grabbed the LiDAR. In 2011, there was a consortium of agencies that flew collecting topographic LiDAR for most of the Northeast. And we took the classified LAS data, extracted the bare earth and the canopy data. So we had 2 different elevation surfaces that we also plugged into the eCognition framework. This is an example of the canopy model on the right. And then we collected field data, again with the partners. We got out there, we got muddy, and collected a lot of training data. So we have lots of point information on habitats. We subsetted the training data, so we had some to train the models, and then we also had some for validation afterward. Through a hierarchical approach, we were able to first understand the mapping extent, because going into this we didn't even know where the marshes were, really. There was some ancillary data, but the old mapping the old maps didn't really highlight all the marshes the same way. It wasn't a consistent product. So we had to go through a process of establishing that mapping extent. And to do that, we developed a tidal surface, so something that characterized mean high or high water. It was a hydrodynamic model. It's something that NOAA puts out, and we've used that to help create a mask. And that was kind of the first step in understanding the extent that we should be looking at. Then we jumped through some coarse level and then finer level classifications, and that got us about 60 to 70% of the way through the process. From there, we had to do some more spatial modeling using GIS. Some of this was still in eCognition, but we did jump out into a standard GIS platform to start to do some modeling. We understood there were certain areas of confusion. We also understood there were certain associations, proximity associations for some of the classes, and we could model those in GIS to improve the product. But of course, it's a remote sensing project, so there's always manual editing at the very end to touch it up, to make it look clean and accurate. And we are always targeting 85% accuracy or better if we can. So here is just an example of what we are looking at for this draft product. And this hasn't gone through the final revision, but on the left is just the image. On the right, you can start to see the level of detail we're getting. This is down to species in some cases, and also just the spatial extent. These are very, very fine features that we're starting to map. And this is going to be done at a statewide scale. So that's quite a bit of work. So what have we learned so far through this process? And again, we're 8 years or so into our high-resolution land cover and habitat mapping efforts. What have we learned? Well, in terms of imagery, high resolution is wonderful, but there are diminishing returns. The higher the resolution, the more processing time and power required, the more confusion. So you don't necessarily need the 3-inch. You could get away with 1/3 of a meter or 1 meter, possibly. Understanding when the imagery was collected. So what season? Are the plants actually in bloom? Are there leaves on the trees? What are you going to be seeing in the imagery? That also plays into the spectral variation. We want to have enough variation there that we can actually generate good polygons and extract good statistics, but we don't want it to be too noisy either. So there are some trade-offs there. Making sure we have enough training data covering all the appropriate classes. This is kind of standard remote sensing classification work. Making sure that have the right field data is key. And then having the expert insights in terms of how to model some of the habitats we're trying to extract, pans and pools and other habitats. Without the input we had from some of the biologists in the field, we may not have been able to model those as well. And then LiDAR is always key. We've done a lot of work in understanding how LiDAR performs in various habitats, in marsh habitats for instance. Down in the southeast where you get these nice, thick, persistent marsh cover expanses, in the northeast it's not quite the same depending on the season that they're flown. Those marshes change, and I imagine you're probably seeing the same thing up here. So understanding when the LiDAR was flown will tell you a lot about whether or not it's actually detecting the ground or if it's detecting a kind of a false ground within the vegetation canopy itself. So what have we done to take all of this data and turn it into meaningful information? Well, we've done a lot, and this is just a quick, I cherry-picked some of the tools and resources that we've put together that leverage our land cover and habitat data. The first two, I'll show you some screen grabs of actual applications. The Land Cover Atlas, the Sea Level Rise Viewer, the Coastal Flood Exposure Mapper, these are all web-based viewers for non-GIS people to go in and actually use our data to make decisions. I was showing Bill yesterday the Sea Level Rise Viewer. There's a component in there that talks about marshes and how marshes migrate and how sea level rise may impact that. We have a story map that talks about how land cover is an indicator for water quality and how you can use that to help decision makers understand potential impacts to water quality. And then we have some actual GIS tools, the Habitat Priority Planner for spatial decision making, non-point source pollution and erosion comparison tools. So these are the tools that allow us to really understand and integrate the land cover data with other information so we can better understand what's happening in watersheds, for instance. So the Digital Coast is a resource I mentioned earlier. The URL is listed up there if you haven't had a chance to explore it. It's a good example of how we, within NOAA at least, and working with other federal agencies, are getting our information out. We're sharing our data and our tools and our trainings through this platform right here. And there are topical areas. So if somebody's interested in climate adaptation, for instance, you can dive into that topic and then understand which data streams and tools are going to be relevant for that particular topic. So it's a nice way to integrate a lot of the information that not only NOAA is collecting and developing, but also stuff from the Army Corps. All of Jennifer's LiDAR data are in the Digital Coast. And we work with other groups like the Nature Conservancy to understand which tools and resources are most useful for them so we can include them here as well. So just in terms of how we're using some of this high-resolution information, here's an example from Saipan out in the Pacific. We did a project that mapped land cover back in 1945. So this is when it was actually built out as a military installation, and what you're seeing is a lot of grasses, and then the white is impervious surface. So you can see how they've really kind of built it out as a military base compared to what we saw in 2005, where that was all let go. It's been completely reforested. It's quite a dramatic change, but the reason we were asked to do that retrospective analysis was because the conservationists on the island wanted to understand where they should be developing protection areas, where they should be conserving land. The areas that used to be forested, for instance down in here, are probably areas where they're going to find some of those legacy species that they want to keep on protecting. And so those areas were able to be protected that way, and of course now they've got a nice snapshot in time from the present so they can understand more things about water quality and other stuff. So another example is we're doing a lot more work with carbon and carbon sequestration. You may have heard of blue carbon. So that's the carbon that may be sequestered by eelgrass, marshes, mangroves, those sorts of areas. And so we're taking a good close look at how these data can be used with various coefficients to understand what are our marshes doing for carbon sequestration and storage. So there's a lot of active research going on here, but we're also leveraging these data products to be able to tell that story. And then I mentioned marsh migration. Through the viewer you can see the current marsh extent. In this case we're looking at Scarborough in Maine. The purple is the current marsh extent, and on the right that's what the marsh may look like with 4 feet of sea level rise, and you probably can't see that there. So here's a blow up. The purples are the existing marsh areas, and then with 4 feet of sea level rise you can see slight expansion and also conversion to open mud flats. Again, depends depends on the hydrodynamics and the water levels. So this is a nice tool for folks to understand where they can start prioritizing conservation areas again, or potential restoration. So where are we going to go from here? Well, we know we're going to continue looking at high-resolution mapping. This is something that everybody wants. The moderate resolution is a great product for the kind of the 30,000-foot level, but when you get down on the ground and need to do some management applications, it's not quite as useful. So the high resolution is something we're going to continue working on. We're also going to continue working on the coastal piece, because that's our niche. And then we have to figure out the balance, though, between we've got this national program and we've got these hotspots for high resolution. One of the things that we've always toyed with was doing more of the high resolution work. When you look at the costs that we're facing, the 30-meter data, to produce that 30-meter data has been on average 77 cents per square kilometer to create. And again, we're doing that every 5 years. We're doing this through partnerships, but that's our cost. When you start looking at 1-meter data, when we were starting to price this out a few years ago, it was on the order of $250 per square mile. That's come down considerably. Within the last couple of years, we're looking at, $19 per square kilometer. In some cases, with the right extent, if we can actually partner up adjacent states to work together and do some cost sharing, we can afford the $2 per square kilometer to do high-resolution mapping. But then you have to consider some of the trade-offs, the classification schemes that people would be looking for, the accuracies they'd be looking for. But this is just to give you an idea of what we're looking at and some of the balances we're going to be considering as we go forward with high-res mapping. And I'll leave it at that.